Hello one and all, welcome to the Math Magic Show. In this one, I'm going to explore the concept of series. I'm going to show you why often in textbooks a lot of the essential ideas are missed, because I think series are placed in the wrong place in most calculus textbooks. They're placed as if and treated like they were one variable quantities, but they're not. They're in fact in two variables because you have x and n, for example. So here I have 1 divided by 1 minus x. On the left side and the right side I have a summation that involves two quantities, x and n. I had the hardest time understanding series, precisely because to me it was like, you have these two different quantities. I don't really understand how they interact a lot of the time, why you change one, what happens with the other. So I thought about it deeply for a long time. I said instead, you know what, I'm just gonna treat it literally as it appears, which is x is one quantity, n is a different quantity, which means really I should be doing this in three-dimensional space, because I have two variables, x and n. That's how I imagine them instead. What I'm going to do first is simply make a graph of 1 divided by 1 minus x, and then we relate that to the graph of x to the n, and you will see how beautiful and magical this is. So I'm going to call this my x-axis. I'm going to have a vertical axis as usual, and because I know 1 divided by 1 minus x, roughly speaking, it looks like this, you see? And then it goes up forever this way. Something special occurs at x equals 1 over here, so it becomes 1 divided by 1 minus 1, which is 1 over 0, which is dne, does not exist. So this value x equals 1, that gives you a vertical asymptote. Let's draw that in there. So I'm going to make this in a different color slightly. So it looks like this. Just as a review, let's remind ourselves, what is a vertical asymptote? It's simply a line that we approach but we don't cross. So I've zoomed in here, and I want to stress the point that, theoretically speaking, because the blue dashed line is a vertical asymptote, the red one should never cross it. So we may draw it this way to suggest that it's going up towards positive infinity up here, and that's fine. But theoretically, there should always be a gap between the curve and the vertical asymptote. Always a gap, even if it's super tiny small. It's always there. It's a good question. What if you actually cross the vertical asymptote? What would that mean? That's for a separate video. Let's go back to our series. So imagine the following, that arbitrarily I choose x equals 1/2 over here. On the x-axis, I choose 1/2. What does that generate? It has a very specific consequence. Take a look. So my series now becomes the series from 0 to positive infinity of 1/2 raised to the n. That's my series. But if I look at this quantity, clearly there is a variable n present in it. So where is that exactly in the picture? It seems to not be present anywhere, until I realize that down here, by saying x has the value 1/2, I can now draw corresponding n-axis just perpendicular to the x-axis. That's bringing us from 2 dimensions into 3 dimensions, so to speak. Well, at least an attempt to show 3 dimensions on a 2-dimensional surface. So when I do that, I can imagine the n-axis as this quantity coming out perpendicular to the x-axis. Also over here, because we're looking at it from a particular angle, you can imagine that this is a box that indicates that it's a 90-degree meeting angle. And now we're going to make use of our series, and let's take a look. So specifically, imagine that n has the value 0. What does that generate? And where do I visualize this quantity? So I would have the following. I would basically have 1/2 to the 0, which is 1. That means along our axis here, where x has the value 1/2, you can also imagine that this represents n equals 0 right here, because you're counting out of the page, so to speak. So n equals 0 is right there. The output was 1, so you can visualize that as simply a kind of arrow that comes up to, say, maybe about here. So when x has the value 1/2 and n has the value 0, you get a 1, indicated by this arrow. When n has the value 1, you have 1/2 to the first, which is equal to 1/2. So where do you show that? Where is it actually present? Well, you set n equals 1, so that means, say, n is over here. This is n equals 1, and the output is 1/2. You can indicate that simply by drawing an arrow that is 1/2 the length of the original one. So if this, I don't even know what color that is, this arrow that you see there is already representative of the 1, then maybe 1/2 of that would be equal to 1/2. You see that? Let's do it one more time. So imagine n has the value 2. Then you would have 1/2 squared, which is 1/4. So then what does that mean? Well, that means, for example, over here, when n has the value 2, that the output is 1/4. So that means you're going to draw a little arrow that is 1/4 of the original arrow. So maybe something small, baby arrow like that, you see? I hope you're seeing how the n-axis is coming out of the page, so to speak, towards us. And then the question is, how does the summation symbol fit into this? Well, it fits into it because what it tells us to is just add up these values to get an approximation for the value of the function itself. So that would be the summation as n goes to 0 up to 2, because our n went 0, 1, 2, of 1/2 to the n, which is 1 plus 1/2 plus 1/4. But we can visualize this sum simply by taking the arrows that we've drawn and just stacking them, because that is what it means graphically to represent addition of numbers. You just stack little line segments or arrows together, and that's what it means graphically to add numbers. So first what I'm going to do is I'm going to take the green arrow, I'm going to stack it on top of this mystery color arrow. So that kind of will go over here. And I'm going to take the light blue arrow and I'm going to stack it on top of the previous two. So that kind of goes over here. And I hope you're beginning to see how it all is snapping together. One thing that stands out clearly, if you look carefully, is that there's still something called an error. In other words, there's a difference between where you got up to and the actual value of the function itself. It's this black line segment right here. That's our error. So that is telling us something important, which is that to decrease that error, I would have to increase the number of terms. In other words, I would have to draw more arrows along the n-axis. This is all of our work. I've zoomed out on it, and I hope you understand that regardless of how seemingly abstract the mathematical concept seems, if you think about it carefully enough, long enough, and so on, there's very likely a way to visualize at least some aspects of it that could be perhaps very insightful and interesting. So for example, when I looked at that series x to the n, I realized it's really something to be visualized in 3 dimensions, because there's an n-axis and an x-axis, and then x to the n is the output from that. So that would be our third value, just the way you see it here with the little arrows. Thanks so much.